Hello, welcome to our TED Talk. My name is Victor Villanueva,
Junior Carranza,
Gabriel Pierce.
and today we'll be talking about the Kepler's 3 laws of planetary motion.
Kepler's first law, also known as the law of ellipses. This law states that all planets move about the sun in elliptical orbits, having the sun as one of the foci. This is the visual representation of the law of ellipses. Here we see the Earth moving in its very elliptical orbit around the sun, with the sun being one of the two foci. An ellipse is a closed curve such that the sum of the distances from any point on the curve to two fixed foci, which here are labeled foci 1 and foci 2, remains constant. So in other words, the sum of the distances is the same for all points on the curve. And no matter where the Earth moves, as shown by the A1 and A2, and also the B1 and B2, which are equal, wherever the Earth moves around in its orbit, the sum of the distances to each of the foci will always be the same.
Kepler's second law, law of equal area and equal time. Kepler's second law of planetary motion describes the speed of a planet traveling in an elliptical orbit around the sun. It states that a line between the sun and a planet sweeps equal area and equal time. Thus, the speed of the planet increases as it nears the sun and decreases as it recedes from the sun. The position of the planet is recorded after equal period of time. When the planet is closer to the sun, it travels faster and covers a longer distance. When it is further away from the sun, it travels slower and covers a shorter distance. However, the amount of area that the planet sweeps in a constant measure of time is always the same regardless of the planet's position to the sun. The area swept is highlighted in green.
Kepler's third law, law of harmonies. This law states that the ratio of the squares of the periods of any two planets are equal to the ratio of the cubes of their average distances from the sun. To give a visual of this rule, if we have two planets revolving around a sun, R1 will be the average distance between the first planet and the sun, and R2 will be the average distance between the second planet and the sun. T1 will be the average period of the revolution of the first planet, and T2 will be the period of the revolution of the second planet. The equation for Kepler's third law is T1 over T2 squared equals R1 over R2 cubed. We can find this equation by first starting with Newton's second law of motion, F equals ma. Since we're dealing with a planet revolving around a sun, we can substitute the gravitational force formula in for F and centripetal acceleration formula in for A. Now, since we're also once again dealing with a planet revolving around the sun, velocity equals change in distance over change in time, which will be, in this case, assuming that the orbit is a perfect circle, t pi r, the circumference of a circle, over t, the period of the planet's orbit. We can plug 2 pi r over t into our equation to get this lovely thing here. And then after solving down a bit, crunching some numbers, we end up getting the period of a planet squared over the average distance of the planet from the sun cubed equals 4 pi squared over g times the mass of the sun. Now, since this ratio between the planet's period and the planet's average distance from the sun equals this, we can assume that a second planet's ratio of its orbital period and its average distance from the sun equals the same thing. Therefore, T1 squared over R1 cubed equals T2 squared over R2 cubed. And after rearranging that equation, we get Kepler's third law equation.
Thanks for tuning in to our TED Talks. Thanks for watching Kepler's 3 laws of planetary motion. And see you next time.